All right, Rachel, Matthew, Laura, Brianne. Here we are to the most favorite subject of all. You only thought algebra was your most favorite subject of all, but now chemistry is your very most favorite subject of all. We are in Module 6 in our book, and I can't do anything about that glare. Maybe I'll try and do something on the next one, but you should be able to see the board nicely. Module 6 is all about stoichiometry. Stoichiometry, which in this chapter, what we're going to do is we're learn to relate the different quantities of different substances in a chemical equation. You're going to find out just exactly how valuable it is, just how much you can do with a chemical equation, that it's actually a recipe for being able to say, okay, if I have this much of this quantity, how much do I have to add to get how much I want of the end result? So it's very, very versatile equations, very important, and you're going to deal with those just exactly like you do with algebraic equations, which is why it's so important to be able to have some understanding of algebra before you're working with chemistry, because that's really the underpinnings for the type of calculations that you're going to be making. If you hear all of these strange scratching noises, that's Sasha who's running around. He's been climbing in the Christmas tree today, and now he's just thumping all around. But stoichiometry is relating the quantities of different substances in a chemical equation. And as we get started in this section, we're going to have chemical equations that have already been balanced for us. But what we're going to move to very quickly is taking a word problem that says, okay, we want to react hydrochloric acid and calcium carbonate to produce such and so. So we have to set it up as a formation reaction, a decomposition reaction. I don't know that we'll do a combustion reaction. I'm sure they probably will, but you have to be able to know what of the three types of chemical reactions you need to set up. If it's formation, if it's decomposition, or if it's combustion, you have to know if it's a complete or an incomplete combustion reaction. You need to make sure that you have your chemical equation balanced. You need to remember what Avogadro's number is. Remember, Avogadro's number is 6.02 times 10 to the 23rd. And we call that a mole, M-O-L-E. I'm not sure I like this orange either. You may need to just do the black instead. But all a mole is, it's a measurement. Like we have a pound of butter, we have 2 kilograms of sugar. A mole is just a quantity. It's this very, very huge number, and that tells us how many atoms of a particular element or how many molecules of a particular compound are contained in a specific mass of that element or compound that has the same mass in grams as that element's atomic mass. So let me go ahead as a quick review and let me pull out for us sulfur, which is element 16. Sulfur has an atomic mass of 34.1, I believe I remembered it correctly. Sulfur has an atomic mass of 32.1 AMUs. And an atomic mass unit is 1.00 times 10 to the something. It's 1.66 times 10 to the negative 24th. And we talked before that 1 AMU is like 1 trillion trillionths of the mass of a housefly. So it's an immeasurable amount to us in the real world. But if you have an atomic mass of 32.1 AMUs for sulfur, if we wanted to find out what a mole of sulfur is, that would be 32.1 grams of sulfur would be equal to 1 mole of sulfur, which would contain 6.02 times 10 to the 23rd atoms of sulfur. And this is what we're going to use our stoichiometry for, is we're going to find out that you can almost think of moles maybe as being cups. Like if you have a cup of sugar, a cup of flour, a cup of sugar, 2 cups of flour, and ½ cup of butter, and you wanted to double the recipe, 1 cup of sugar would become 2 cups. 2 cups of flour would become 4 cups. ½ cup of butter would double to 1 cup. And that's the type of relationship that we're going to be able to do with our chemical equations. And that's what I'm going to get right into right now. I do want to look briefly at page 162, and I want to read this to you. So you learned in the previous module, relating the quantities of different substances in a chemical equation is called stoichiometry, and it is probably the single most important concept in this entire course. Read this module carefully, thoroughly. We'll constantly go back to the concepts presented here. You must be firmly grounded in the subject matter to be able to proceed in this course. Just like he said earlier, if you haven't yet understood and gotten very, very comfortable with scientific notation, which this is scientific notation, if you haven't learned that, you have got to go back and learn it. Whether you use a YouTube video, you talk to me, you find something on the internet, but you've got to have scientific notation, and you've got to be very, very, very comfortable with the material from Module 6, which is stoichiometry. And it says chemical equations are the same as mathematical equations. We've talked about that. If you can do something to a mathematical equation, you can be able to do that same thing to a chemical equation. And just like when you're solving a mathematical equation, you can solve with the variable on the right-hand side of the equation or on the left-hand side of the equation. Do the same thing in a chemical equation. Let's see. Now from chemical equations we have the reactants on the left-hand side of the equation. We have the products on the right-hand side of the equation. We don't have to have, just always be given the reactants. You can take that product and back solve it to say, okay, if I ended up with this much water, how much hydrogen did I start with, and how much oxygen did I have to start with to get that much water? So this stoichiometry is a very, very useful principle, I guess, of chemistry. So let's look at this. We're going to look at page 164, example 6.1. A chemist forms ammonium sulfate, NH4 twice, SO4, which is an excellent fertilizer by combining ammonia and sulfuric acid. If the chemist ends up making 12.2 moles of ammonium sulfite, how many moles of ammonia were used? Now, when you guys are studying, you have to go through your text, you have to read it, you have to do your best to understand what he's saying. I am going to show you a different way to do the arithmetic or to do the algebra here to relate moles to each other. And I think you'll find it very, very straightforward. And once that clicks for you, you're going to be saying, you mean that's all there is to this? Yes, that's all there is to it. It's very, very simple. It's just the way that it's written out here. It looks hard because he's talking through it and he's using unit conversions and things, because as far as I can tell now, it's not likely that a lot of you are going on to higher levels of chemistry and science, so we can use this, and it's still a solid way to understand, a solid way to teach what we're doing. So he's going to form ammonium sulfate. Let me get my little markers here so they can tell how far over I can go. I can go over that far, and I'm going to start here. And I can go up that high, can't I? Okay, ammonium sulfate by combining ammonia and sulfuric acid. Ammonia is NH3, and you will quickly learn that ammonia is NH3. sulfuric acid is H2SO4. H2, I'm sorry, yeah, H2SO4. And sulfuric acid is something that shows up a whole lot in chemistry. So if we're combining ammonia and sulfuric acid, I need to have enough space here so that I can balance the equation. So my reactants, ammonia and H3 plus sulfuric acid, H2SO4, those will react together and they will produce ammonium sulfate, which is NH4 twice SO4. Let's make sure that we can see all of that. Yes, we can see all of that. Ammonia plus sulfuric acid yields ammonium sulfate. Ammonia, sulfuric acid, yields ammonium sulfate. Ammonium sulfate, which is a fertilizer. Now, I think that from your knowledge and from your understanding of algebra, that you would know that what this means right here in parentheses with the subscript of a 2, that we're going to take this NH4 and that there are actually 2 of those, so that you actually have N2H8. So when you're counting to make sure that your equation balances, you actually have 8 hydrogen here. You have to be aware of that. So the first thing that we're going to want to do is see what we need to do to bring our equation in balance. We have one nitrogen here, 2 nitrogens here. Let's see what happens if I have 2 molecules of ammonia. 2 nitrogen, 2 nitrogen. I have 2 times 3 hydrogen, which is 6 hydrogen, plus 2 hydrogen is 8 hydrogen. Well, over here, I have 8 hydrogen, and I have 8 hydrogen here, and I have 6 plus 2 is 8 hydrogen here. I have 1 sulfur, and I have 4 oxygen. So our equation is balanced. I'm going to go ahead and move this a little bit closer, since we only had to have 2 NH3 plus H2SO4 yields NH4SO4. Let me see what I want to tell you. What we're going to find out is something very, very, very cool. What this tells us, see these things here? These are actually called stoichiometric coefficients. I'll tell you that in a minute. But our coefficient here is a 2. That's an understood 1. And this is an understood 1. And the relationship that we're going to be trying to comprehend here and trying to utilize is the one that tells us, okay, if I have 2 moles, these are moles, 2 moles of ammonia are going to produce 1 mole of ammonium sulfate. Also, 1 mole of sulfuric acid, which is H2SO4, that's also going to be necessary to make 1 mole of ammonium sulfate. So this is really just a relationship. We have 2 to 1. If we have 2 moles of ammonia, we're going to end up with 1 mole of the fertilizer. If we have 1 mole of sulfuric acid, it's going to result in 1 mole of the fertilizer. All a mole is a quantity. Just don't get hung up on the mole. Now the question says right here, if the chemist ends up making 12.2 moles of ammonium sulfate, which is the fertilizer, how much ammonia did he use? So, do we really need to do anything at all with the sulfuric acid? No, because we're not talking about sulfuric acid. All we're talking about is the ammonia. And you see how we've got this 1 here? It's just like the understood one. If you have x plus 3x, you know that you have 1x. We don't need to write that 1 there. It's what we say is redundant. It's being used twice. So what we have here tells us that if we start with 2 moles of NH3, what we're going to end up with is 1 mole of ammonium sulfate. So the ratio or the relationship between these is 2 to 1. Now, if we have a ratio of 2 ammonia to 1 hydrogen sulfate, I'm not sure why I said hydrogen sulfate, ammonium sulfate, let's go back and see what are they really asking for. How many moles of ammonia were used? Okay, we want to find out how many moles of ammonia. How many ammonia were used to make 12.2 moles of ammonium hydroxide. What we're seeing here is heavy, heavy, heavy vocabulary, simple, simple, simple arithmetic, because we have a very straightforward relationship between 2 ratios here. I'm looking for what I did with my marker. Okay. And we're simply saying 2 is to 1 as what is to 12.2. We're converting from a fraction, or we're coming up with equivalent fractions. 3/2 can be written as a fraction over 6 by multiplying by both sides by 3, right? I mean, numerator and denominator by 3. 3/2 is the same as 9/6. That's all that we're doing here. Now, the easier way to do it, rather than, you can say 1 times what is 12.2? What's 12.2? So 2 times 12.2 is going to give us 24.4 moles of ammonium hydroxide. And you're going, huh? That's all there is to it? Yes, that's all there is to it. We're just changing from one fraction to another. We can also we can cross multiply. 1 times x is x. X is equal to 2 times 12.2. X is equal to 24.4 moles of ammonium hydroxide are necessary to have in your recipe if we want to end up with 12.2 moles of that fertilizer. Okay, let's see. Can you see that? Yes, I think you can see that. Okay, that's so straightforward, so easy that it's almost scary. Let's try another one so we can see if we're actually doing this right. Well, actually, let's look at this. What's the coefficient of sulfuric acid? 1. So 1 mole H2SO4. What's the coefficient here? It's 1. 1 mole of H2SO4 results in 1 mole of ammonium hydroxide. So if we wanted to end up with 10 moles of the fertilizer, how much sulfuric acid do we need? Duh, 10. Because you have 1 over 1 is equal to x over 10. X is 10 moles of ammonium hydroxide. Very straightforward. Do not be afraid of this section. Let's look at number 6.1 on your own. 6.1. Chemist performs the following reaction. This is 6.1, page 165. 6.1. 2NaNO2, which is a solid, reacts with a gas of oxygen to yield 2NaNO3. Now let's make sure before we go on, we don't want to assume that this equation is balanced. 2 sodium, 2 sodium, 2N, 2N. 2 times 2 oxygen plus 2 oxygen gives us 6 oxygen. 2 times 3 oxygen is 6 oxygen. So this equation here is balanced. The question is, how many moles of oxygen gas must the chemist use in order to make 15.0 moles of NaNO3? So what we're looking for is the relationship between oxygen and our end result, between oxygen and I don't know what, sodium hydroxide, I don't know what that one is. Well, you have 1 mole of oxygen producing 2 moles of our final product, NaNO3. The question that's being asked is, how many moles of oxygen? We don't know how much oxygen we need. How much oxygen is necessary to give us 15.5 moles of our product? Here we have our relationship. 2x is equal to 1 times 15.5. Divide both sides of this equation by 2. X is equal to 7.75 moles of oxygen. It's very, very basic, straightforward arithmetic. It's just understanding the relationships between the products and between the reactants. I'm looking for on your own problem. Oops, I cannot divide. 15, it's supposed to be 15 moles. I said 15.5. 15.0 moles, which would be 7.5 moles of oxygen. Now, remember, I've been asking you guys, requiring you guys to be specific with your significant digits. So if we're given 15.0, right here there are 3 significant figures. So for significant figures, we would have 7.50 moles of oxygen, ratio of 1 to 2. There's half as much oxygen as there is this second product. The second part of this question says, how many moles of NaNO2 are necessary? Well, let's look at this. We have a relationship of 2 to 2. What's 2 over 2 equal to? That's right. If you have a relationship of 2 NaNO2 resulting in 2 NaNO3, it's a relationship of 2 to 1, so you have a 1 to 1 ratio. So you're going to need, if you want to end up with 15.0 moles of NaNO3, you're going to have 15.0 moles of the NaNO2 to begin with. So that's what we're talking about here. Let's go ahead and move on to page 166, where we're talking about an experiment where we limit reactants. And I must have missed a page because I want to talk about limiting reactants. Let me see. Okay, limiting reactants. Having a hard time keeping up with my caps this morning, but it is Saturday, so I'm allowed to. What happens is, let's say, I'm trying to think. Well, let's say that we're making a recipe, chocolate chip cookies, and we have 2 cups of butter and we have 5 cups of flour. And we want to make a double batch of cookies. So we have 2 cups of butter and we have 5 cups of flour and we have 6 cups of sugar. Now hang with me on this because I'm trying to make a real life comparison here. This is what we have on hand. So this would be, in chemistry, this would be the reactants on hand. Or in our cookbook thing here, this is how much butter we have in the pantry, how much flour we have in the pantry, how much sugar we have in the pantry. And here's our recipe. Recipe for cookies. So we need 1 cup of butter. We need 2 cups of flour. And we need 2 cups of sugar to make our recipe. And we want to make absolutely the most number of cookies that we possibly can because all the guys are coming home from college and we know they're going to eat us out of house and home. So we think, okay, what can I do? Well, I've got 2 cups of butter. So that's enough butter for 2 batches. We have 2 cups of butter. If I need 1 cup of butter for 1 batch, I need 2 cups for 2 batches. Okay? Now, 5 cups of flour. How much flour do I need? 2 cups for 1 batch. So for 2 cups, I have enough, for 2 batches rather, that would be 4 cups. So I have enough for 2 batches, plus I have 1 cup left over, right? How much sugar do I need? I need 2 cups of sugar for 1 batch. How much sugar do I need for 2 batches? Well, I need 4 cups of sugar. But I've got 6 cups of sugar. So I have enough for 2 batches, plus 2 more cups. Now let's go through and analyze this. How many batches of cookies can I make? Well, I can make 2 batches of cookies and only 2 batches of cookies. Well, how can that be? Because a batch of cookies only needs 2 cups of sugar, and I've got 2 cups of sugar. Well, yes, I do have 2 cups of sugar, but it also needs to have a cup of butter. I don't have any butter left. It also needs to have 2 cups of flour, and I only have 1 cup of flour. So this butter is the limiting reactant. It says we only have so much butter. And once we use that butter up, it doesn't matter if I have more flour or if I have more sugar. I can only make that smallest amount because it's sort of like this is sort of like your greatest common factor. Okay? This is what we're talking about when we have limiting reactants. What's going to happen in your chemical equations is that when the reaction takes place, you're going to run out of something before you run out of the other thing. And that's something that's really important. So, page 166 is an experiment that Miss Haley will do with you in class, where we're talking about limiting reactants, and it has to do with the amount of gas that's produced when you react baking soda with probably vinegar. You have baking soda with vinegar, which reacts to form carbon dioxide, which you capture that carbon dioxide in a balloon, and the balloon gets bigger, and then it gets a lot bigger, and then you add some more, but it only doesn't, the measurement isn't hardly changed at all because you've run out of one of the reactants. Would have been like you ran out of the butter, and it didn't matter if you added more of the other stuff. You weren't going to get any more carbon dioxide. You weren't going to get any more cookies because you didn't have all of the ingredients necessary. So, and that experiment demonstrates the concept of limiting reactants. When there's more than one reactant in a chemical equation, one of those reactants usually runs out first, which stops the entire reaction. When we ran out of butter here in our cookie recipe, couldn't make any more cookies, could we? Because we didn't have what we needed. And that's all that they're talking about when they talk about limiting reactants. So, a limiting reactant limits the amount of product that can be formed in a chemical reaction. Makes perfect sense. When you don't have your supplies anymore, you've got to stop working. Page 166. We're in fully analyzing, did I say 166? I mean 168. When we've been working in algebra and using one equation to solve another, we can typically only find one thing from one equation. But what you learn with these chemical equations is that you have one specific set of relationships and you can learn many things from it. And it's what we're going to be working with in Module 6. For example, okay, we have a reaction right here, and we're going to have magnesium and hydrochloric acid. We have magnesium, and we add 1 mole of magnesium, we add 2 moles of hydrochloric acid to that, and our result is 1 mole of magnesium chloride and hydrogen gas. Okay? Magnesium, which is a solid metal, hydrochloric acid, which is a liquid, is going to give us a water solution, an aqueous solution, and that's also going to react in the presence of oxygen. Give us an aqueous solution with some leftover hydrogen gas. Aqueous is just water-based. So, this tells us that the above reaction, I'm reading right in the middle, 1 mole of magnesium. So 1 mole of magnesium plus 2 moles of HCl. So that says, let's say that we have magnesium and we wanted to make sure that we used up all of our magnesium. How much hydrochloric acid are we going to need? Well, it says that the relationship between magnesium and hydrochloric acid is 1 to 2. So if we want every bit of our magnesium to be used up, we're going to have to make sure that we have 2 moles, or a quantity, of hydrochloric acid that is equal to the mass, twice the mass in grams of the atomic mass of this HCl. Just review this one more time. Hydrogen should be 1.01. 1.01. Chlorine is 35. 35.5. Our significant figures here are limited to 1 decimal point, so we have 36.5 grams is 1 mole of hydrochloric acid. But it says we have 2 moles, so we're going to double that. Multiply that by 2, 36 and 36 is 72, and 1 is 73 grams of HCl. If we have 1 mole of magnesium, what is magnesium? The atomic mass, Lm, magnesium, it's number 12, it's 24.3. So if we have 24.3 grams of magnesium, that's 1 mole. Remember, this says we have 1 mole. A mole is the mass in grams that matches the atomic mass of the element magnesium. We found the element magnesium here, which was number, I forgot it already, magnesium number 12. Here's magnesium. That number below it, 24.3, that's the atomic mass. So you take that atomic mass, an amount in grams, that's 1 mole. So if we have 24.3 grams of magnesium, and we want to make sure that we react every single bit of this magnesium, we have to have 2 moles of hydrogen chloride, which is hydrochloric acid, I'm sorry, I think. And it's irrelevant if I'm correct by saying hydrochloric acid or not. But that means that we have to have 73 grams of HCl to use all of this up. What happens if I'd only have like 50 grams of it? Well, I wouldn't have enough to use up this magnesium completely, so I'd have some magnesium left over. That's what we're talking about, complete reactions and limiting reagents. Okay. And of course, we can use this magnesium to tell us how much magnesium chloride is formed. The relationship between magnesium and magnesium chloride, 1 mole of magnesium gives us 1 mole of magnesium chloride. So it's a 1-to-1 relationship. It's going to be exactly the same. Example 6.2 on page 169. You can look through that. I want to go ahead and do do on your own problem number 6.2, which is on the very top of page 170. And I'm just going to talk through this by having ratios and relationships. Okay, page 170. The first step in a long process that converts iron ore into pure iron involves converting iron ore into iron oxide. So this is iron ore, Fe, which is iron, S2. So it's iron and sulfur in combination. In the presence of oxygen, 11O2 yields iron oxide, FeO3 plus SO2. I don't remember what SO2, it's irrelevant. 8 SO2. Let me walk over here and make sure that we can see this. 8 SO2. All right. So this is our reaction. This is problem 6.2, and we're on page 170. Because we have coefficients other than 1 in front of these elements and in front of these reactants, I'm going to assume that the equation is balanced, but that's a dangerous thing, so let's verify. Okay, we have 4 iron on the left side. We have 2 iron on the right side. Did I miss something? Yep, I did. 2 Fe2. And how did I know that I'd missed something? What made me think I had miscopied? Because as I have it written, 2 FeO3, I only have 2 atoms of iron. But I have to have 4. 2 times 2 is 4 iron. 4 times 2 is 8 sulfur. So I have 8 sulfur, 8 sulfur. 11 times 2 is 22 oxygen. 2 times 3 is 6 oxygen, plus 8 times 2 is 16 oxygen, gives us 22 oxygen. Our equation is balanced. And you need to always make sure that you have your chemical equation balanced. Okay, now what's our question? If an iron manufacturer starts with 1,256 moles of iron ore, how many moles of oxygen will be needed to react completely with the iron ore? Okay. If we're going to react, why did I erase that? 4 iron S2 plus 11 O2 yields 2 Fe2 S Fe2O3. This is really an annoyance. Plus 8 SO2. Let me make sure I've got this back. 4, 11O2, 2, 4, 6, and 16. Okay, this says that the iron manufacturer is starting with 1, 2, 5, 6.0 moles of iron ore, which is FeS2. How much oxygen does he need to react completely with this? How much oxygen do we need? And how many moles iron oxide, Fe2O3? Got a couple of different things going on. First it says we're going to have 1,256.0 moles of the iron ore. Well, we need to know how much oxygen we have to have for that reaction to take place completely. We do have a beginning relationship. We say if we have 4 moles of iron ore, that it takes 11 moles of oxygen. Love to know where that Z came from. Of oxygen. Now, if we have 1,256.0 moles of iron ore, how much oxygen do we need? Cross multiply. 4x is equal to 11 times 1,256.0. How are we going to solve for x? We're going to divide both sides of this equation now by 4. The 4's cancel, and we have 11 times 1256.0, that quantity divided by 4. So we see that we are going to need to have this many moles of oxygen. Let me get my calculator out. And we have 11 times 1,256 divided by 4. 3, 4, 5, 4, okay? I missed my decimal point. 11 times 1,256 equals divided by 4. 3, 4, 5, 4. 3, 4, 5, 4 moles of oxygen. Now, do I have the correct number of significant digits? Well, no, this is an exact relationship here. We're going to look at the number of significant digits on the iron ore. There are 5 significant digits, so we're going to use 5 significant digits here. And we have that the amount of moles, the number of moles of oxygen that we need is 3,454.0 moles. Now let me look back here and make sure that I'm not leading you all astray. 3,454.0 moles of oxygen. So it's just this simple relationship here. So we've solved the first part of our problem, 3,454.0 moles. Now, how many moles of iron oxide are going to be produced? Well, now we're going to look at the relationship between iron ore and iron oxide. So let's erase this and see what we have for the relationship between iron ore. So we have 4 moles of iron ore that will produce 2 moles of iron oxide. We can even reduce that relationship. So we have, it's a 2-to-1 relationship. 2 moles of iron ore produce 1 mole of iron oxide. So if we have 1,256.0 moles of iron ore, how much iron oxide are we going to have? Cross multiply. 2x is equal to 1256.0. Going to divide that in half, and we're going to end up with our very basic result being, if I can get to my answers, going to divide that by 2, and we have 628.00. X is equal to 628. Why is it 628.00 moles of iron oxide? That's right, it's because of the significant figures once again, significant digits. 1, 2, 3, 4, 5. We only have 3, 628, so we add 0.00. The way that, you can look back in the back answers where it goes through how to solve these on your own problems. You can use their method. Of course, it's the right way, but if you can end up concentrating on ratios, it's so much easier. A ratio of 4 to 2 is the same, 4 to 2. Reduce that a ratio of 2 to 1. If you end up with 1256 over here, how much did you have to start with? That's all there is to it. This is what I meant when I started talking at the beginning of this lecture about how straightforward it is. This is one where they've made it a lot so that it looks a lot more complex. So I'm going to go ahead and stop. That's page 170 because that's a long enough lecture for now.